Okay, so let me again explain the plan for today. So the plan will probably consist of two parts. So part one will be this thing that I mentioned yesterday. This is this BFM construction of symplectic duals in some generality. I'll say in a moment what is the generality. And second is going to be, let me say it like this, let me say motivation and partly upgrade from quantum field here. Okay, let me say what this is going to be. So here we're going to deal with the following situation. So unfortunately, I'm going to use the same notation as in our papers, and the notation is a little bit awkward for historical reason, but I'm already kind of used to this notation, so I'm going to stick to it. So what we want to do is to start the following situation when G is going to be some reductive, let's say, connected algebraic group. And let's take M, which is going to be a symplectic finite dimensional representation of G. And we want to take X to be the Hamiltonian reduction of M by G. So let me remind, this includes all Quiver varieties. And we want construction of X check in this case. So in fact, I'm going to do it under some additional assumption, which should not be necessary, but so far we will not. I mean, there should be some kind of upgrade of this to general M. So I'm going to assume that M is the cotangent bundle. Well, it's a symplectic representation, so a symplectic linear representation. So I assume it's cotangent bundle some N, where N is any representation. Now, one thing I want to stress right away is that the construction will really depend. So, the construction will not depend on X as a variety, but it will depend on this data, and it will depend on. Well, I mean, the way I'm going to say it will depend on N and G. In fact, it will only depend on N plus N star, which is the cotangent bundle. But the point is that we really need this data of group in the representation, and not just this symplectic reduction. So, and in fact, there are, for example, in the Quiver case, there are many known examples when you can take this, when the same Quiver variety can be obtained from different Quiver data, and or more precisely, you can write the same X as a Hamiltonian reduction of some representation in many different ways. For example, if X is a point, you can write it in like infinitely many ways as a Hamiltonian reduction of different groups. And this dual will really depend on this very heavily. So for instance, dimension of this dual will always be twice the rank of G.
But is it the case that for your construction you need it to be of the form T star n, or can you do that?
No, I can't. Unfortunately, I mean, I can. Well, I won't have time to discuss it. So it's it really has to do with some kind of possible upgrade of this story of motivic Donaldson-Thompson variance. But which I can't do so. I mean, actually, in some way maybe I can, but in some different way. But again, I won't get there. But the actual construction I'm going to explain will really explain this. Will be really based on this, and then I'm going to sort of try to explain some language somehow from field theory somehow, which will also sort of explain this construction and also give maybe some kind of upgrade of it. Okay, so let me explain this construction. So it might sound, yes.
If M is 0 dimensional,
That's a good case.
could you tell example with what will be X check?
Okay, let me start. Well, okay, I can do it right away. So I can, okay, let me first give you a fancy answer. Fancy in the sense that will be sort of literally a special case of what I'm going to say next. But then this fancy answer can be computed just what it is. Okay, so this is very easy to say. So okay, so I'm taking the case when M, or well, same as N, is 0, and G is arbitrary. So then the claim. Well, okay. Remember that in the framework I'm talking about, all varieties are affine. So this is supposed to be some affine variety, some kind of possibly singular symplectic, but in fact in this case it will be non-singular. It will be some non-singular affine symplectic variety. But well, first I'm going to just construct as an affine variety, and then I'm going to tell you what the answer is. You will see that well, you will definitely see that it's symplectic. So the constructions. So I'm going to construct the algebra of functions on this variety. In this case, and the algebra of function is equal to the equivariant G of O equivariant homology of the affine Grassmannian of G. Remember that the affine Grassmannian is equal to G of K or G of O, where K is C of T of T square brackets of T. So this thing is an algebra. And it's not, well, it's homology, so the algebra actually has nothing to do with the cup product, but it's an algebra with respect to convolution. It has a convolution, so it has some kind of convolution product. Which in the usual way is commutative. And you can actually compute what you get, and in this case, so there's a theorem of Misha and Roma from 10 years ago, which says that X check is what's called the universal centralizer. So X check consists of pairs X, let's say in G, or well, in the Langlands dual algebra, and G in G check, such that Gx G inverse is equal to X up to conjugacy, and also the requirement that X is regular. So, for example, an exercise in one senses that it has dimension twice rank of G.
So is this a phase space of the total lattice?
Sort of, yeah, but let me ignore this. Good. Yeah. So one thing I want to mention is that this thing. So when I was talking about this stuff yesterday, I wanted things to be conical, and this guy is actually not conical. And so in general, so I said that somehow the construction is more general than the conical thing. In most cases, this thing actually will be conical. We can actually say in terms of this original representation, it's easy to. So this construction, the construction of X check I'm going to present, this X check I'm going to construct will always have a canonical C star action. So here it's just C star action is the same as a grading on a algebra of functions, and this here it's the homological grading. But it's not conical with respect to it. And in general, for given n, I can tell you from right away, from the very beginning, there's some condition on n so that the dual is conical. So it basically says that n should be sufficiently big. So 0 is not sufficiently big, so it's not conical, but the construction doesn't use that. Yes.
But you cannot take 0. No multiplication by scalar. But you cannot multiply by 0 because it will condition particularity.
I'm sorry?
I say it's not conical. You have action of C star.
Yes.
But you don't have action of C.
Yeah, there is no 0.
Yeah.
No, I mean, it's just, this thing is great. I mean, this thing is graded. This thing is graded, but just it's not. I mean, conical basically means that somehow you want grading to be non-negative, and you want to have zero, just one-dimensional space in degree 0, and that's not the case here. No, I mean, what they said is kind of right, but somehow you have to. I mean, what they said doesn't literally make sense. So somehow, but you have to. I mean, if you make sense of what you said, then it will be right.
Sorry, can I ask, do you know when, for instance, this the dual is going to be also of the form like?
Of this form, no. I mean, I think like it's in some sense wrong. I mean, almost the idea is that almost never. And like statistically, this is not supposed to happen. It's just. No, if you have a quiver, even for quiver varieties, it usually doesn't happen. So if you have like finite or affine quiver of type A, this will happen. But if you have finite or affine quiver not of type A, this will not. This will not be the case. Okay, let me actually. So then, since I already told you this, let me tell you what is the general construct. Yeah, by the way, so maybe one remark about this. So somehow this, that's again an exercise, or maybe something between an exercise and a homework problem to show that this guy has a canonical symplectic form. But I can also, let me explain what it is from this point of view, because this will become more general. So somehow I want to construct a Poisson structure in this algebra. So and kind of best way to construct a Poisson structure is actually to define a quantization. So if I have a non-commutative deformation, in particular, I get a Poisson structure. In fact, this X check will always come with a canonical quantization. And so here the only question is where to write it. So let me maybe write it here. Quantization of C of X check. This is going to be, I should take the same thing, but I should take the homology equivalent with respect to C star, where this C star acts by loop rotation. So it acts by rescaling T. So the claim is that in that case this thing becomes non-commutative. So this you lose commutativity of the product, and this is actually non-commutative algebra. Which so this I mean everything here is going to be a module of the corresponding covariant parameter. So in particular, there will be covariant parameter corresponding to C star. So this is going to be algebra. This is an algebra over what we call C of H bar, where this H bar is the generator of equivalent homology of C star, of the equivalent homology of point with respect to C star. And so it's a quantization in the sense, well, it is filtered quantization or whatever. Yeah, maybe one more thing that I wanted to say here is that if you look at this universal centralizer, it has a canonical. It carries sort of a canonical integrable system. So this X check canonically maps to this G check mod adjoint action. In fact, if you want to be completely canonical, well, it doesn't really matter very much, but let me take G check dual here and also put dual here, G check. You can, well, I mean, it's kind of obvious from this presentation. This is just projection to X. And what is it in these terms? I mean, in this term, somehow we're supposed to map the algebra of functions here into this, and this is just a equivalent homology of a point. So this corresponds to embedding of H star. So any kind of equivalent homology of cohomology of anything, this is always module of equivalent homology of a point. And so G of O is homotopically the same as G. So we have this, and so this is and this is the same. This is always okay. I actually got a little. Yes. So this is always the same as functions on the coadjoint quotient.
Quantization
well, it's just, I mean, you can write this thing as some kind of Hamiltonian reduction of the cotangent bundle, and then it will be kind of quantum Hamiltonian reduction of differential operators. I don't know. I don't have anything better to say. I mean, that's actually a way to see why this thing is symplectic, because a priori, when you write this universal centralizer, it's not completely obvious why it is symplectic. But the reason it's symplectic is you can write it as a Hamiltonian reduction of the cotangent bundle. Okay.
This is the standard construction of the quantum product.
Yeah, but let's let's not discuss this now. Let's discuss this later. So okay, now what do you do for general case? I mean, well, general case you can kind of upgrade this construction. So let me just say that, well, it will be convenient for me to say it in the following language. It will be convenient to say that, so this thing I can write as formally as homology of kind of double quotient g of k mod g of o mod g of o. So this is some kind of stack like this. So I'm going to define such a stack for general Gn. So now we have Gn. So I'm going to define a stack which I'm going to denote by Sgn, which will actually map canonically to this stack. So in fact, I can actually, the stack will be a secretly quotient of some in scheme Rgn by g of o. And so this Rgn will be some in scheme which will leave over the Grassmannian. So yes. I think equivalent homology is so homology. Well, actually, in general, it's supposed to be Braverman homology, which in this case doesn't matter. But Braverman homology is just homology of the dualizing sheaf. Equivalent homology of any sheaf is a module of equivalent homology of a point, cohomology of a point.
Yeah. So equivalent homology of
Cohomology of the. Yeah, there's no equivalent homology of a point. I'm saying equivalent Braverman homology of anything is a module of equivalent cohomology of the point.
It's the same as equivalent cohomology. What's the answer?
But I don't see why this question is real. I never mentioned equivalent homology of a point. Oh, you mean no? That it's the same. Okay, right. So it's the same as equivalent cohomology because again, equivalent homology. Well, okay. So well, for a complete variety, equivalent homology is the same as by definition equivalent cohomology of the dualizing sheaf. For a point, dualizing sheaf is just constant sheaf in degree 0. So. Well, I mean, it's an. Okay, I mean, again, let's ignore this question. I mean, it's just, definition is the. I mean, again, I don't want to be completely formal. I mean, for me, homology of a double quotient is by definition this. And
It's the emphasis not to shift, so that's not.
right. So somehow, no. I mean, the sheaf is kind of infinite. But again, so it's just easier for me to formulate the answer in this way. But okay, if you want, it will be just longer to say. I will take just equivalent homology of some in scheme here. Without thinking, but it will. But I mean, after some shift, I mean, this is really absolutely irrelevant question. So just so definition of this is this. I don't know. I personally don't know any other definition. So okay. So now what is the stack going to be? So so the stack is the following, and then well. To make Dennis happy, I will also say what this guy is. So the stack consists of the following. Well, let me give a modular definition. So this Sgn consists, it's a modular space of some quadruples. Let's say P1, P2, kappa, and phi, where P1, P2 are G bundles on the formal disk, so this is spec of O. So kappa is an isomorphism between P1 restricted to the formal punctured disk. So if I stop here, then this is literally the same as this stack. And phi, this is a common, so let me write it and then I'll explain what it means, common n-valued section of P1 and P2 on D. So what does this mean? So first of all, if I have a representation of my group, I can make any principal bundle, I can turn any principal bundle into a vector bundle using this representation. Then I can take a section of this guy on D and section of this guy on D. And then since I have identified them on a puncture disk, I can require that on the puncture disk, these two sections coincide. That's what I mean by common section. And so note that if my representation is 0, then there's nothing here. So somehow that I got the same thing as before. And so now the claim is that, okay, so, well, and what is this RGN? Well, just, again, to make Dennis happy, RGN corresponds to trivializing one of these bundles. On D, no, on D, on D. That's important. So it's like, yeah, I mean, this RGN, which is an int scheme, this same data, but let's say P1. Let's say that P1 is trivialized. Same data plus trivialization of P1. Well, and again, to make Dennis happy, let me just say that. No, you okay? This is.
So this means that there is no P1, right? There is just a P2 and
No, but I mean, this data and this data is still non-trivial.
Yeah.
No, right. I mean, so this is well, I want to say that this is equivalent Borel-Moore homology of this stack, but again, this is by definition G of O equivalent Borel-Moore homology of this guy RG. So what I claim, and things are a little bit infinite dimensional here, but what I claim is that first of all, you can actually define this thing. That's really not a very difficult task, and moreover, this has a natural convolution product. Has natural convolution product. So what I want to say, one remark I want to make is that, so how does this map look like? This map, so it's kind of trying to be a vector bundle, except that it's not. So it's every fiber here is a vector space. And it's actually going to be, well, infinite dimensional, but it doesn't matter. It's a vector bundle over every GFO orbit on the Grassmannian. But in fact, this vector bundle is canonically, this RGN, it sits inside the Grassmannian times N of O. So, and every fiber is actually going to be a fiber of every point is canonically a subspace of finite codimension in N of O. But it's this codimension, it's constant in every G of O orbit, but otherwise it jumps. So therefore, homotopically, this thing, for example, is equivalent to the Grassmannian. So if I don't put this Borel-Moore homology here, if I put ordinary homology, then it will be just the same as homology of the Grassmannian, and then I don't get anything new. But Borel-Moore homology is not homotopically equivalent, fortunately. So somehow, I do get something new, and so that's well, it could seem like a little bit crazy construction, but the claim is that this is the right construction. So what it means is the following. So let me tell you a few statements. So first of all, it satisfies, well, it conjecturally satisfies everything I said yesterday. So and parts of this we can prove, but also maybe what's more interesting is that we can, and I said that using this construction, Ben Webster, in a very big generality, proved this categorical Kazil duality. But I want to format another statement that actually, I mean, this might seem again a little crazy, but actually, in more or less in all cases, you want to compute. In all cases, when you have an expected answer for the symplectic dual, you can actually verify that this expected answer is right. So let me format one statement. So let me assume that I have a Quiver, that I start with Quiver data for finite type quivers. So just a second. And then, yeah, so assume that we have Q is a quiver of ADE type. That's just, this is just going to be one example of calculation. So we fix V and W are two dimension vectors. And then, so I put G to be this product of GL VI. And, well, and then there's a representation NVW, which I basically defined last time. So let me not repeat it, so it doesn't really matter what it is right now. Last time, but it was that our X in this case is in the Nakajima quiver variety. And again, to make my life simple, just to be able to formulate the answer relatively quickly, I'm going to make some assumptions. So now I'm going to define GQ. This is the corresponding group, let's say a joint group of corresponding to this quiver. And I'm going to define as, yes, the weight lambda, which is summation Wi omega I. And I'm going to define mu, which is lambda minus summation Vi alpha I. And I'm going to assume that mu is dominant. In fact, I can give you the answer without this assumption, but it will be just longer to explain what it is. So in fact, this dominance condition will guarantee that the dual is conical. And then a theorem is that in this case, X check is what I called last time double lambda mute. So this is the transversal slice to. So here this again affine Grassmannian, but it's affine Grassmannian for a different group, which appears to for this group GQ in GQ lambda bar. So here is an interesting remark. Yes.
Sorry, I'm just badgering a dumb question, but there's no sense in which I can then run this procedure backwards to recover my original quiver.
No, this is not that I know of. I'm sorry? To the spec, well, it's spec of that algebra, yes. Well, I mean, I don't know how deep it is, but
Was it known before?
no. Well, again, not that I, no. I mean, this is written now in the second. We have a series of 3 papers with Misha and Nakajima, and this is more or less the subject of the second paper. Well, at least that's proven in the second paper. And so maybe a remark, which is partially addressed in Misha's ICM talk, is that note that everything here, so here I said that Q was a quiver of finite type. But in fact, this guy is now defined without this assumption. So this X check is defined formally for any Q. So that gives a definition, well, some kind of definition of these transversal slices in the affine Grassmannian for every quiver, not necessarily. And you can actually, for quivers of affine time, you can also do some computations, and you can actually say what you get. But at least in some cases, so there's some kind of modular description of what you get. But in principle, it's defined as absolutely for any quiver. So you can try to be brave and formulate some conjectures, which I'm not going to even write, that here, for example, this thing has a crucial property of this thing is that if I take its IC sheaf, then if I take its hyperbolic stock at 0, this is canonically isomorphic to the corresponding to the weight space in the corresponding representation, and this statement now makes sense for any Q. And of course, it's sometimes known in the fine case. Beyond the fine case, it's probably never known. But the statement makes sense.
Is this algebra finitely generated? Always?
Yes, I mean, maybe I should say this. So this algebra is, okay, so this C of x check, it's always, so this x check is always in a, so this C of x check is always, okay, well, let me say what is known in general. So this C of x check, the way it's defined, it's always finitely generated, integrally closed, well, integral and integrally closed. So x check is a normal variety. Closed, well, it has a, so dimension of this x check is always twice the rank of G. Now it carries a canonical integrable system which goes to G mod adjoint G. This is integrable system. So what else? Okay, let's see. 1, 2. Yes, and it's always birational to the cotangent bundle to the dual maximal torus quotient by the Weil group. And there are, well, some other things you can show about this, but maybe let me not go into this because I wanted to talk about something else. Maybe let me mention one thing. So in our symplectic duality, remember that last time I had the space S sub x and T sub x, and symplectic duality sort of one crucial property was that there was somehow under symplectic duality it was supposed to be interchanged. So let me give you something which has something to do with it. Let me tell you something which has something to do with it. So namely, suppose that let me remind you, one of the spaces had to do with Hamiltonian automorphisms of X. So how can I produce Hamiltonian automorphisms of X in this situation? Well, the way I can produce it, suppose they have some group which I'm going to call GF. This again comes from physics because F is flavor, and this is called flavor symmetry in physics. So suppose that GF is just some other, let's say, reductive group. Suppose that GF sits inside automorphisms of N over G. Then, of course, GF acts on X. Remember, this was N plus N star Hamiltonian reduction by G. So if it commutes with G, then it acts on the reduction. And so now, what does it tell me in terms of how they see in terms of X check? Well, then GF is also going to act X on my, let's say, RGN. And I can replace, and therefore I can consider the equivariant homology not just with respect to G of O, but G of O times GF of RGN. And this gives me deformation of the original algebra. So, okay, so let me continue. Let me pretend that I'm on a torus. So this way I get a deformation of X check over what? Over the adjoint quotient of this. And that's kind of what we want. Well, if we replace, for example, here GF by its maximal torus, then we get just deformation over the Cartan subalgebra of GF. And that's kind of what we wanted, because somehow we wanted to see that anytime something acts on X, then we want to see a deformation of the dual over the same base. This is how you see it, for example, here. Now, maybe another thing I want to mention is this Poisson structure. Poisson structure is defined exactly the same way as before. So there's a canonical quantization.
And so, if you compute H2 of this X check,
does it have have anything to do with the...
No, X-check, it doesn't make sense to compute X2 of this X-check, because, I mean, H2, it makes sense to compute H2 only for a resolution. This is the affine guy. So it's like typically conical, it's you know, it's homotopically trivial.
H2 quantization of X-check.
I mean, like Hochschild H2, well, no, okay.
Does it have anything to do with endomorphisms of M over G? Because
I don't know. I don't. Well, I mean, this is a good question. No. In some sense, I mean, it does have something because, I mean, I said that if this, well, at least this kind of automorphism, they produce a deformation, and they produce deformation for the quantization as well. So, therefore, so the produce. I mean, it produces this deformation of this guy is a Poisson algebra, but also it produces deformation of the quantization. So, so definitely
So
has.
the question is whether the right of this H2 is...
Right. I mean, but again, I mean.
endomorphisms of M.
Yes, but I don't know. So let me just say that everything, there's a quantization. Quantization just means that we consider everything C-star equivariantly. And well, there are many other things I can say. So for instance, there are many other cases when you can compute the answer, and actually in all of these cases you get, I mean, basically, anytime you know what you want to get, you can prove that's what you will get. But also often that seems like to be kind of completely new variety. So there's a conjecture you can formulate that the result is that this X-check is always symplectic singularity. So somehow it's always Poisson and it's always generically symplectic. I don't know in general. I mean, it's a conjecture. In general, it's a symplectic singularity in the sense in Baville's sense, which I explained yesterday, but I don't know whether this is true, but I mean, I do believe that this is true, and this gives like a very big source of examples of this. I mean, if this is true, this gives a big like source of examples of the symplectic singularities, which typically are not going to have a symplectic resolution.
Is that case when it's equal to G star to each other?
Mod double, yes, this is when n is the adjoint representation.
And is it known whether this for G equal SA2?
Well, you can write it, I mean, it's known in the sense that you can write this algebra by generation relations. I mean, yeah. You can write you can write the algebra by generation relations. Yes. Okay. So there are many, again, like I said, so there are many things I can say about this construction, but instead I want to switch to this kind of. I have about 20 minutes left, so I want to switch this QFT inside. So I will probably only have time to do this, what I promised, what I called yesterday, linguistic introduction. And but let me at least try to do that. Okay. Any other questions? All right. Let me. Then what do I want to erase? Okay. Let me erase it. So. Okay. So QFT inside. Okay, so here, I mean, I won't have, as I said, I'll most probably not have time to talk about what quantum field theory means in this context. Although this we can at least partially do this. But so I'm going to treat it as a black box. So somehow the black box will be the following. So somehow so physics study three-dimensional n equal 4 supersymmetric quantum field theories. And so, again, Pasha, let's do it later. Now, well, I mean, by black box, I mean that somehow I'm going to tell you a little bit, in a moment, I'm going to tell you to what kind of data you're supposed to associate this thing, and then what you can do with this mathematically, but somehow what sort of. So there will be an input and output, but in the middle there will be some kind of magic machine which will produce the output from the input. And again, if I had more time, I could try to demystify this machine a little bit, but I won't have time for that. So, so what physics study? Physics study modular space of vacuum in this theorem, and the full modular space of vacuum. So this is, let's say, M, which is modular space of vacuum. Which is, in general, going to be kind of a complicated and pretty badly behaved space. But this modular space of vacuum, and this is precisely where kind of supersymmetry comes in, has some kind of two special pieces which are kind of much better understood than the general, than the whole modular space. And so the two pieces are called Higgs branch of the modular space. Let me call it MH and MC. This is called Higgs branch. And sorry, and this guy is called the Coulomb branch. And these guys are supposed to be, well, possibly singular symplectic varieties.
So what's the relation between M and MH?
Well, I mean, well, at least in nice situations, they're supposed to be, they sort of, well, you should more or less think about, it's not precisely true, but more or less like nice situation, there are going to be some specific components of it. So this is going to be some variety with many components, so there's some specific components.
Sorry, I kept quiet. If it's not a gauge theory, what do you mean by Higgs and Coulomb?
No, I mean, thesis define it without,
No.
yes, no, yes.
Right.
Just, it has absolutely nothing to do with gauge theory. This is just about supersymmetry algebra. Just somehow, gauge theory is absolutely irrelevant here. No. I mean, if you look, for example, this Guyot-Witten paper from 10 years ago, the main theory they study, which they call TOG, is unless GSGLN is not a gauge theory at all, but they like the whole paper is devoted to studying this theory for exceptional groups, and which is like as far from gauge theory as possible. No, it's just not true.
What's the definition of the word Higgs and Coulomb?
Let's not do it now. I mean, I don't want. I mean, we can do it afterward. It's just you consider this as vacua which are killed by some particular supersymmetry charges. And really, gauge theory is absolutely irrelevant here. So, well, and the idea is that these guys are supposed to be symplectic dual. And in some sense, more or less, all known, it is, if you believe in what physicists say, then all known symplectic dual pairs come from this construction. Now, let me kind of play the following game. So I promised to say to what data you're supposed to associate such theories, but I'm going to say, well, a little bit of this, and also what kind of operations you can perform with this theory. So somehow, first of all, well, the simplest data, okay, so game, some QFT game. So this will be just a bunch of so-to-say facts. Fact number one is that you're supposed to be able, so if X is a symplectic variety, in fact, not even affine, but somehow, but let me just for simplicity assume that everything is affine variety, then to this you're supposed to associate some theory Tx, such that in this case the Higgs branch is going to be equal to X and the Coulomb branch is a point. That's one thing you can do with theory. Another operation, kind of trivial operation you can do with theories, but in a moment I'm going to do non-trivial operations. If T1 and T2 are two theories.
Tx doubles also is just a theory.
I'm sorry? Yeah, yeah, but by T, for now I'm going to, the letter capital T is going to denote a theory. Then you're supposed to be able to define T1 times T2, which is a product of these two theories, which just on all of Higgs and Coulomb branch corresponds to just taking product. So product, and I won't even write, so somehow here you're just supposed to multiply this MH and MT. Now, next operation is called mirror symmetry.
I'm sorry, Sasha.
Yes.
So before, you made this point about how knowing X wasn't enough. I kind of needed to remember this kind of more of this presentation.
Yeah.
So similarly here, you really just get by with X, or are you thinking of
No, here X is not, I mean, the quotient of X, the symplectic reduction, that's a different, maybe I should, let's call it Y and not X. I mean, that's not necessarily the same X I was talking about before. So the theory really, when I write this something by symplectic reduction, that's really, I mean, the data of the symplectic, how I write it as symplectic reduction, this is what the theory tells me. Actually, that's kind of. I'm sorry?
This is G equals point.
Yeah, this is sort of G equals point. Yes, I mean, yes, I'll come to G. The G will come like in a minute. So, but before G, I want to say that there's a notion of 3D mirror symmetry. So mirror symmetry, which is just given a theory T, you're supposed to construct another theory, which I'm going to call T star. It will later also be T check, such that MH T star is equal to MCT, and MCT star is equal to MHT. So that's
Star is
yes. Now comes the well. Okay, let me say 4.5. I'll explain what why, or maybe 3.5 rather. It's because it will be half of 4. So given G, which is a reductive, say connective group, there should be theory T of G such that its Higgs branch of T of G is equal to the nilpotent cone in the Lie algebra of G, and the Coulomb branch of T of G is equal to nilpotent cone in the Lie algebra. Now, why?
Moduli space, the union of these components, or there are some other components?
No. There are definitely more components somehow. In this case, unless G is GLN, I don't really know. I mean, like nice situation is that if there is a almost bijection between symplectic leaves, then more or less it's going to be components of the form. The components will be like symplectic leaf of one times the corresponding symplectic leaf of the other. But in this case, as you know, the story is more complicated. So somehow, I don't know what is the full modular space in this case. It's a valid question. I mean, it is a valid question actually. Well, no, I mean, let's discuss it. Not in this case. I mean, in some cases, yes, and in the case I was talking about, in the case when this BFN construction works, nowadays there is a mathematical definition due to Kevin Castella, but I won't talk about this. I mean, I will have to. So the half is the following. So why? I mean, this is something which I'll have to postpone. This theory has additional structure. So this theory it's supposed to also have G symmetry. So somehow it has, or physicists would call it flavor symmetry G. So it has flavor symmetry G, but I haven't said anything about this yet. So let me talk. So I'll get back to this. And flavor symmetry already produces some kind of non-trivial thing on the level of, at least on the level of Coulomb branch. So somehow, let me talk a little bit about the symmetry. So somehow there is a notion. So this is number 5, I guess. There's a notion of a group acting on a theory. So I think I need. So let GF be, let me say again a reductive group. Now there's a notion of GF of theory T with GF symmetry. And again, for now, we don't know what theory is. We kind of using it as a black box, but we can only see it from this Higgs and Coulomb branch. So I should tell you what kind of structures it imposes on the Higgs and Coulomb branch. And I'm going to tell you only what kind of structure it imposes on the Higgs branch. And the Coulomb branch, I'll say it in 2 minutes, because on the Higgs branch, somehow it corresponds to just GF action on Hamiltonian GF action on MH, and something on MC. And I'll tell you what this something is in a moment. Before that, I want to say one more thing. So the only question is that now I'll have to erase something. So I'll have to erase this.
Sorry, before the GF action give you a definition of MC, but now it's not
it gives a deformation. Okay, it does give a deformation of MC, but it gives. I want more than that. So well, I mean, I want a much richer structure, which in particular will imply deformation, but will be a much bigger structure. And I'll say it in a minute. So 6 is that if group, well, let me say just I'll just write G instead of GF. If G acts on T, then I should be able, there's a notion of gauging asymmetry. So you can gauge the symmetry, which means that you produce another theory, which is no longer going to have G symmetry, but it's just going to be a new theory. And this new theory is going to be denoted by like this. And in terms of the Higgs branch, what is its Higgs branch? The Higgs branch is just the Hamiltonian reduction of the original guy. And MC is, well, of T of G, well, sorry, of T quotient by G is something. And, you know, at this point, I'm not in a position to tell you the answer, because for this I have to explain what happens here. Then I'll be able to tell you what happens here. So, and now what? And the last thing I want to say is there's also a notion of S duality, but this is just I'll just mention this for completeness. There's the S duality. S duality, it gives you somehow, it's if you have a T theory with G symmetry, it produces another theory, T check with G check symmetry. And there's actually a formula for this guy in terms of all the previous structures, although from this formula it will be absolutely unclear why G check acts on the result. And I'll just write it again, this formula for completeness. This formula was originally due to Guyot and Witten, but in fact I can explain what it has to do with some mathematical structures, but I won't have time to do this again because I only have 5 minutes left. So the formula is that this T check is equal to the following. I have to multiply T by T of G. Then I have to gauge the diagonal action. And then I have to take the mirror dual. That's kind of, well, that's actually, I'm not going to use this part 7. I just wanted to say that because it's just for completeness. But so if you want, you can ignore this. Okay, so the main thing I want to do is I want to explain this and relate it then to what I did before. Now, maybe before this, let me just say that, so one thing we can do is that if M now is a symplectic representation of G, then we can, well, to this M, particularly M is symplectic manifold, symplectic variety. To this, we're supposed to associate a theory, but also if it carries an action of G, we can gauge this G symmetry, and we get a new theory like this. So these theories are called gauge theories. This is what physicists in this constants mean by gauge theory. And in this case, by what I said before, its Higgs branch of this T sub M with G gauged, this is equal to M reduction by G. And the point is that, and that will be part of what I'm going to say, if I'm going to say it in more, well, in this setting, but the idea is that this construction which I explained should say that MC is X check defined 20 minutes ago. But also, I want to get back to this because I want to at least say something about this theory T of G. But again, I want to say that, well, okay, we'll get back to this. So I have like 5 minutes left. Okay.
So this can't possibly be an operation on MC to pass to M.
No, it's not an operation on MC. It's just it's some additional structure. Well, this you'll see in a moment. I'm not sure you're going to like it, but you'll see it.
While you're racing, so when NH is singular, then what do you mean by this hyperkähler reduction?
Well, it's not. Well, just well. I mean, so far, right now I'm treating this in a naive sense. I mean, I'm only going to care about shapes when all the varieties are affine, and then I take this reduction in this kind of categorical sense. No, but you're right that actually somehow in the true world you're supposed to treat this as a kind of DG stack rather than. But I'm not going to do it. I mean, like, if you want to construct honest theory, that's what you should do. But I'm not going to do it. Okay, now let me tell you the answer to this question. What kind of structure, what kind of additional structure, so the phone MC is supposed to be imposed by symmetry. So again, and I'm going to suppress this F letter. So okay, so G acts on T. Now consider the affine Grassmannian of G, and consider the derived category of G of O equivariant constructible sheaves. This category has been studied a lot. For example, somehow there's a paper of Bezrukanik of Finkleberg and Mirkovic where it's somehow it's completely described, and well, which in fact description is really due to Drenfeld. So I'm not even going to tell you well, I won't have time to tell you what the category is. But the only thing I want to say about this is monoidal categories, and the monoidal structures again comes from convolution. Now, if you have a monoidal category, you can study ring objects in this monoidal category. And so the statement is that G symmetry on T should imply a construction of some A, let's say G T. This is a ring object. In fact, this ring object should also be Poisson in the appropriate sense, but let me not go into this ring object in, well, let me call this category C, in C, such that its Schrieg stock at the point 1 in the Grassmannian is the algebra of functions on MC. So it's a remark that if you have well, it's easy to see that if you have a ring object in this category, if we consider its stock at 1, Schrieg stock at 1, it has a ring structure. Well, of course, from this it's kind of clear that in the correct world you should treat everything as kind of DG objects, and I'm only kind of taking cohomology. But let me again hide this under the rug. So somehow, like in good situation, everything is going to be formal. So somehow we're not losing anything. But in principle.
For which theory?
No, for this, so somehow you start with the theory T. Well, MC, let me say MC of T. So the structure that we need is this. So, and the structure that we need is this ring object, and
So how do I go from the ring object to the deformation?
well, before that, let me say something else. Let me say how to go from the ring object to MC of the gauge theory. So that's so 6 is that MC of T reduction G is going to be equal to the cohomology, well, G of O equivariant of the Grassmannian of this ATG. To answer your question, the point is that you can actually treat this Schrieg stock as an object of a equivariant derived category of a point with respect to G, and then you should take its cohomology on the point. That will be the deformation. Let me know. If you take this Schrieg, if you have an equivariant object of derived category here, if you take its Schrieg stock, it's going to be an object of equivalent derived category of point with respect to G of O, and then we can take its cohomology there, and that will define a deformation.
You need spec of
Spec, yes. Oh, let me write like this.
So in your example that you started off today, can you say to me,
Yes. Before that, let me give you another example somehow, which you may like more. And this is, let's go back to this theory T of G. So we don't know how to construct the theory yet. Because, well, I actually didn't say what it means to construct the theory, but let's still somehow here, we want this MH to be the nilpotent cone, and M Higgs, MC is the nilpotent cone of G, and this is nilpotent cone of G check. So this guy is supposed to have G symmetry. Now, on this level, this is fine. So somehow it has an action of G, right? So we want to construct now a ring object on the affine Grassmannian of G whose Schrieg stock at 1 is equal to functions on the nilpotent cone. Now, I'm sure that you know what this object is. Yes. So the point is that now in this case that's a rare situation when it's perverse. So in this case, this AGT, this is an object of this is a perverse G4 equivariant sheaf on the Grassmannian, and this by geometric Satake, this is the same as the category of representations of G check, and AGT is the regular representation. So it has the property that its Schrieg stock at 1 is equal to functions on the nilpotent cone. And by the way, the deformation in this case is going to be, you just deform the nilpotent cone to all of G. So in this case, if you take what I said before, if you take this Schrieg stock, treat it as an equivariant object of the equivariant derived category, take its cohomology, you get functions on G. Okay. So now, last thing I'm going to say, I'm already over time, is that the construction I presented earlier today sort of fits into this framework. So there you can actually construct a ring object. And the ring object is very easy to construct. But again, unfortunately, I can only do it in this cotangent case. So somehow, so now we say that given G and M, which is symplectic representation, we're supposed to construct some, well, let me call it in this case AGM, which is a ring object on the Grassmannian of G such that its cohomology should give me functions on the Coulomb branch. And now, I mean, this should work for any M. I can only do it for now. So in the cotangent case, assume M is T star N, where N is any representation. But I can do it in this case, but also in this case, I can check that there is a, you see, the same M, I can represent this cotangent bundle in many different ways, possibly. I can check that it's independent of that. So somehow, but the connection should be canonically attached to M. And well, this is very easy. So I have this RGN, which I explained. So this maps to the Grassmannian. So let's call this map pi. So this A is just going to be the direct image of the dualizing sheaf. Well, I have to be careful about what you mean by it, but there's really no problem. I mean, you have to sort of normalize everything in the correct homological degrees, but there's no problem here. And so it's easy to see well, it is easy to see that this guy this is a ring object. And see, originally I said that it's a Braverman-Moore my algebra was Braverman-Moore homology of this guy. So this Braverman-Moore homology, so it means that it's just cohomology of this dualizing sheaf. So it's obvious that now if I take this guy, its cohomology is what I said before. So this is a ring object, and it's equivariant if G of O equivariant cohomology on the Grassmannian. That's the same as, well, by definition, more or less, G of O equivariant Braverman-Moore homology of this RGN, which is what I started with. No, it's stock at 1 is, no, in this case it is, yeah, in this case it is real, but that's what it should be, because its stock at 1 should be functions on the Coulomb branch of an ungauged theory, and in that case it was a point. Yeah, in this case it is. Yeah, I guess I should stop here.